Hi, this is Hilal. In this video on Mathematical Economics series, we will learn about the bordered Hessian method of optimization. Okay, so this bordered Hessian matrix method is used to optimize an objective function. Okay, where there are two inputs. Let us say we have an objective function like this. We have f of xy. Okay, this is our objective function. Okay, we want to optimize this very objective function, and we have two inputs here, x and y. Okay, this word optimization means because in real life there are always limitations, what we call the constraints, which we have to take into the consideration, and we have to maximize if we have a utility function or minimize if we have a cost function with certain limitations. Okay, so in this video we will build a mathematical derivation example of a utility function. Okay, we will try to maximize a utility function from the consumption of two goods. Let us say we have the two goods x and y, and obviously with the constraint of income and prices of the goods. Is, let us say we want to maximize our utility function, that is f x y. Okay, and to this utility function, let us say we have the constraint of the income, that is g x y is equal to m. Okay, that means we want to maximize our utility function subject to the budget constraint. Okay, in parallel I will give you an example also. Okay, let us say we have a utility function. I will write here, we have utility function like this, u of x y. That means we want to maximize our utility function from the consumption of two goods x and y, and they are related like this. We have 2 times xy. This is our utility function. Okay, and we have a budget constraint here. Let us say we have a budget constraint like this, 3x, such that 3x plus 4y is equal to 90. Okay, so we have an objective function and a constraint function. We want to maximize our utility with the budget constraint. Okay, 3 means the price of good x, 4 means the price of good y, and here this 90 is our income total. Okay, so we want to maximize our utility with the limitation, with the constraint here. Okay, and generally we write it like this, p1 x plus p2 y is equal to m. Okay, now how do we maximize or optimize an objective function with constraint? For that we use the Lagrange's method. Okay, so here I will draw the Lagrange's method. Okay, forming the Lagrange's function is simply we just set this constraint function equal to 0 first. Okay, if we set it equal to 0, so it will become m minus g x y is equal to 0. Okay, after that we multiply this constraint with lambda. Okay, so first we set constraint equal to 0 and multiply it by lambda. So here we have this constraint, we will set it equal to 0 and multiply by lambda. So this will become 90. If we transpose all the terms, this will become minus 3x minus 4y, okay, is equal to 0, and to this we will multiply by lambda. I am just skipping some steps here to save the space. Okay, so first step in what we call for the first order condition for optimality is we will form the Lagrange's function. Okay, so after that what will we do? We will form Lagrange's function by, I will denote Lagrange's function by L is equal to, we will add our utility function and the resulting constraint function to form the Lagrange's function. So our utility function will be, what is our utility function? That is f x y plus lambda, we have m minus g x y is equal to 0. Okay, so first step was set constraint equal to 0, multiplied by lambda. After that we form the Lagrange's function by adding the objective function with the resulting constraint function. Okay, so I will not set it equal to 0 here. Okay, so here what will happen, our Lagrange's function will become L is equal to our utility function is 2xy, 2xy. To this we will add this Lagrange's this resulting constraint, that is lambda times 90 minus 3x minus 4y. Okay, this is our Lagrange's function. Okay, so first we need to use the first order condition. Okay, first order condition. And by the way, what is meant by this very utility function here? So we have the utility function u is equal to, let us say, 2xy. It can be thought of it can be thought as the complementary utility function. So the goods are here complementers. Why they are complementers? If we consume 0 units of x, then our total utility will be equal to 2 into 0 into y. Okay, so our utility is when we multiply any number, any variable with 0, so this will become 0. Okay, so this means these two, x and y, are complements. Why? Because if we consume only y and none of the x, our utility will be 0. Okay, similarly, if we consume 0 units of y and all units of x, and in that case also our utility will be 0. So they are the complements here. And what is the utility derived here? So the utility derived, I will write here like this: u is equal to 2xy. That means we need to consume the goods in pairs. Okay, so if we consume 1 unit of x, 1 unit of y, our utility will be 2 into 1 into 1, that is 2. If we consume 2 units of x, 2 units of y, so 2 into 2 is 4 into 2 is equal to 8. Okay, that means if we consume 2 units of this x and 2 units of y, so 2 to the 4 to the 8, our utility will be 8. And as I told you, if we consume 0 units of x, then our utility will be 0. Okay, because 2 into 0 into y is 0. That means the utility function, that goods are here complements. Okay, I hope I am making myself clear up to this now. Now what we need to check the first order condition. Okay, first order condition is checked by partially differentiating the Lagrange's function with respect to x, y and lambda, and setting them 0 simultaneously. Okay, so first order condition will require that we need to partially differentiate this Lagrange's function with respect to x, y and lambda. So L subscript x means partially differentiating this utility function with respect to x. Okay, so this will become that the derivative of this will be d f x y with respect to x. Okay, so here since the derivative of x is 0 here, because we have a constant m, so we are left with minus lambda, and the derivative of this function with respect to x, so this is d g x y upon dx. Okay, and we set it equal to 0. And what will be the derivative in our example? So L of x, L x means partially differentiating, so I will write here, we are just checking the first order condition here first. So differentiating this utility function with respect to x partially, so what is the derivative of x? It is 1, so we are left with 2y here. So okay, so we have 2y. And what is the derivative of x here? 1. since first and last term they are constants because we are partially differentiating with respect to x, so we are left with only with minus 3x. So the derivative of x is 1, so we have minus 3 into lambda, so we have minus 3 lambda, and we set it equal to 0. Okay, so we were just partially differentiating with respect to x. Now we need to partially differentiate with respect to y, so it will become d f x y over dy minus lambda d gxy, and differentiating it also with respect to y and set it equal to 0. Okay, so here we have in the numerical portion L subscript y means differentiating our Lagrange's function with respect to y. The derivative of y will be 1, so we are left with 2x, and similarly we are left with the derivative of y will be 1. All these two are the constants here, so we are left with minus 4 lambda. Okay, minus 4 lambda, and we set it equal to 0. After that we need to differentiate partially with respect to lambda. Okay, so if we partially differentiate with respect to lambda, our utility function, sorry, this Lagrange's function, since no lambda is involved in the first term, so the derivative will be 0. What is the derivative of lambda? It is 1, so we are left with m minus g x y, and we set it equal to 0. And here in numerical portion we have L of lambda is equal to, now what is this is our Lagrange's function. Since no lambda is involved in the first term, so derivative will be 0. The derivative of lambda will be 1, so we are left with 90 minus 3x minus 4y, and we set it equal to 0. Let this be our equation first, equation second, equation third. Okay, after that what we need to do, since we have solved this for the partial derivative of x, y and lambda, we need to find the optimal values of x, y and lambda here. Okay, so we can do one thing here. If I want to save the space, so these are the equations. If I just manipulate them here, okay, like this, so let it equal to be 0. Let us say, no, I will not, it will get, you will get confused here, so I will let it as they are. So it is equal to 0 is equal to 0, and this is also equal to 0. Okay, now if we want to solve them, let me solve these things here. Okay, so we have 2y minus 3 lambda, 2y minus 3 lambda. Let me again rub this. I can write 2y is equal to 3 lambda if we transpose it on the RHS. So in the first equation we have 2y is equal to 3 lambda. In the second equation we have 2x is equal to, if I transpose, this will become 4 lambda. Okay, and I will not do anything to this third equation. I will just divide these two equations here. So we have 2y upon 2x, 3 lambda upon 4 lambda, lambda gets cancelled, 2 and 2 gets cancelled, so we are left with y upon x is equal to 3 upon 4. Okay, or we can write here y is equal to, if this is 3 upon 4, if we transpose, this will become, this will get multiplied, so this is our value of y is equal to 3 by 4 x. And what we need to do here, we just need to put y is equal to 3 by 4 x in equation third. So I will write, put this value in third equation. Okay, so what will be our third equation? So third equation will become 90 minus 3x minus 4. In place of y we have 3 upon 4 and x, and set it equal to 0. This 4 and 4 will get cancelled, and we have minus 3x. Minus 3x is minus 6x. Okay, so we are left with, am I doing the calculation right? I guess I am doing the calculation right here. So we have uh, 90 minus 3x minus 3x is equal to 0, or 6x minus 6x is equal to minus 90, or x is equal to 90 upon 6. So we have 6 ones are 6, 6 fives are 30. So the optimal value of x is 15. Similarly, we need to put x is equal to, so we got x is equal to 15. Just plug x is equal to 15 again in equation third. Okay, put x is equal to 15 in equation third. So I will write it in equation third. So we have 90 minus 3 in place of x, we have 15 minus 4y is equal to 0, or we have 90 minus 45 minus 4y is equal to 0, or we are left 90 minus 45 is equal to 45. So which means uh, 45, if we transpose this 4y here, this will become plus 4y, or y is equal to 45 upon 4. What is 45 upon 4? So we have 4 ones are 4, 4 ones are 4. Again we are left with 1. Okay, here we will form this decimal, so this will become 10 here. So 4 2s are 8, so obviously we will get y is equal to 11.2. Okay, so the optimal value of y is equal to 11.2. We are just first deriving the first order conditions. Okay, we are not touching the bordered Hessian method up to this now, because for bordered Hessian method will be used in this video for checking the second order condition. Okay, so we got the value of x is equal to 15, our optimal value, y is equal to 11.2, and similarly we can calculate the value of lambda. Okay, we just plug x is equal to 15, y is equal to 11.2 in our third equation. Okay, I will write it like this to get the value of lambda. Sorry, we will not put it in the third equation. We will put the value of x is equal to 15 or y is equal to 11.2 in either of the first two equations. Okay, let us put x is equal to 15 in first equation to get the value of lambda. So we have, sorry, in second equation, because x is in second equation, so we have 2 in place of x, we have 15 minus 4 lambda is equal to 0. Okay, 2 15s are 30, so this means 30 is equal to, if we transpose, this will become plus 4 lambda, or lambda is equal to 30 upon 4. Okay, so what is 30 upon 4? So we have 4 7s are 28, 2 are left, so this will become 20, 4 5s are 20. Okay, so we got the value of lambda is equal to 7.5. Okay, now what is meant by this lambda? This lambda is also called the shadow price. Okay, it tells us how much our utility will change if we increase 1 unit of the budget. Okay, it simply tells what will happen to our utility if we change the constraint by 1 unit. Okay, this lambda tells us, okay, it simply tells us what will happen to our utility if we change the constraint by 1 unit. Let us say if it was 90, if it becomes 91, what will happen to our utility? Okay, so this is called the shadow price. Also, it tells us what will happen to our utility when the constraint changes by 1 unit. Okay, so we got the optimal values of x, y, and lambda. These were the first order conditions. Now we need to check the second order conditions. Okay. So this optimization up to this does not mean that the utility is at its maximum or minimum. It only tells us that we can afford the goods x and y, okay, with the income and price, but we don't know whether we are at the relative maximum or minimum. For that we need to check the second order condition. Okay, so how do we check the second order condition? Let me rub this out uh, to make space here. Okay, now to check the second order condition, we will form a matrix, what we call the bordered Hessian matrix. How it is formed? Let us write Hessian matrix. H bar is the Hessian matrix. Bordered Hessian matrix is formed by, I will write here, we have 0 on principal diagonal. Okay, first we write the second order partial derivatives, or I will first form the Hessian. How is Hessian formed? I will show you here. Hessian is determinant composed of second order partial derivatives. Okay, with second order direct partials on the principal diagonal and second order cross partials of the principal diagonal. What is meant by this? It is simply we have L x x L x y L y x L y y. Okay, first we form the Hessian matrix, and Hessian matrix is a determinant composed of second order partial derivatives. Okay, these are all second order partial derivatives with second order direct partials on the principal diagonal and second order cross partials on the non-principal diagonal. Okay, this is our plain Hessian. This is not our bordered Hessian. Okay, and what is the bordered Hessian? Bordered Hessian matrix is simply our plain Hessian matrix, which is bordered by the first derivative of the constraint with 0 on principal diagonal. That is, we have 0 on this principal diagonal. Okay, and this Hessian is bordered by the first derivatives of the constraint. What is our constraint? This is our constraint. This is our constraint here. Okay, so we have gx, I will write here gx, we have gy, we have gx gy. Okay, I'm just showing you how we form the bordered Hessian matrix. Bordered Hessian matrix is formed by, firstly we take the plain Hessian. Plain Hessian is composed of the second order partial derivatives with direct partials on principal diagonal. This is called the principal diagonal, and cross partials on the non-principal diagonal. Okay, and this plain Hessian, when bordered by the first derivative of the constraint and 0 on the principal diagonal, then we call it the bordered Hessian matrix. Okay, this is our bordered Hessian matrix. I have shown you how do we form the bordered Hessian matrix. Okay, now what we need to do here, because we are checking the second order condition, first order condition will not tell us whether our utility is at maximum or minimum. Okay, it only tells us we can afford these two values at x is equal to 15, y is equal to 11.2, but it doesn't tell whether it is maximum or minimum. For that we need to use the bordered Hessian method, method. Okay, as I have told you how to follow this. Okay, now what will I do here? I'm just getting short of the space. That means I will rub this here. Okay, I will rub this here to solve this very bordered Hessian method, or I will just put it here to make it more suitable for you. So I will write h, this is bordered Hessian, is equal to, and I have told you how we form this. We have 0 gx gy gx gy. Okay, so our Hessian is bordered by the first order partials of first order partials. Excuse me, I someone is calling me, so let me go there first. I will come again here. Okay, so we write this plane Hessian here, that is lxx lxy lyx and lyy. This is our border Hessian matrix. So for that we need to rub this out to make the space available here. Okay, now what is we have 0 here, so I will write 0. Okay, what is the derivative of this constraint function? Since this is g xy, that means we partially differentiate this constraint function with respect to x. So the derivative of x is 1. Since no x is involved, so it is here 0, it is also here 0, so we are left with 3 here. So in place of gx we have 3. Similarly, gy differentiating partially with respect to y, since y is here, the derivative of y is 1, we are left with 4 only. So we have 4 here, that means here we have also 3 and we have 4 here also. Okay, now this was our the derivatives, first derivatives of the constraint. Okay, now what is lxx? Okay, so here we have calculated lx was this very thing. That means we need to differentiate this Lagrange's function again with respect to x. That means we need to take the second order derivative. Okay, so second order derivative means simply lxx will be lxx means differentiating again with respect to x, since no x is involved here. Okay, so no x is involved here, so the derivative of this is 0, this is also 0, so lxx is 0. Now what is lxy? That means again differentiating this very function with respect to y now. So that since y is involved here, the derivative of y is 1, so lxy will be 2 here. Okay, now what is lyx? lyx, so differentiating this very function with respect to x, so we have x here, so derivative of x will be 1, so we are left with 2 only. Okay, so we have 2 here. And what is ly? Y means differentiating this function again with respect to y, since no y is involved here, so derivative will be obviously equal to 0, so we are left with 0. Now just inserting these very values here, so we have 0, lxy is 2, lyx is 2, and lyy is 0. Okay, now what we call this, the order of this bordered principal minor is determined by the order of the principal minor being bordered. Since we are bordering a 2 by 2 Hessian matrix. Okay, so this h represents the second bordered principal minor. Okay, so I will write this is called second bordered principal principal minor. Why it is called second bordered principal minor? Because this principal minor, which is 2 by 2, since the principal minor being bordered is of dimension 2 by 2, so we also call it H is equal to H2. Okay, H2. This is called the second bordered principal minor. It seems confusing, but it is not confusing. Why? Because the order is determined by the order of the Hessian we are being bordered. We are bordered. We try to border. Okay. So now we need to find the determinant of this H2. So what will be the determinant? So we will take the determinant of this bordered Hessian matrix. So how do we take determinant? So we will take determinant along first row. So we have 0 here. Okay, so 0. Now what will we do? We will delete this row and this column and multiply the resulting determinant. So 0 into 0 is 0. So we have 0 minus 2 to are 4. Then we have this is plus. Then we have minus 3. I have shown you in the matrix method how do we form the, how do we take the determinant. First term is positive, second we take negative, and in this case we mentally delete this row and this column and take the determinant of the remaining elements. If we delete this row and this column, so we are left with 3 2 4 0. Okay, now 3 into 0 is 0, minus 4 into 2 is 8. Okay, then we have plus, deleting this row, this column and this row and taking determinant of the resulting determinant. So we have 4 here. So we have 3 2s are 6. So I will write here 6 minus 4 zeros are 0. Okay, now what will we get here? So let us write. We are left with minus 4. Now we have 3 into minus 8 is 24, plus 24. Okay, we have 4 into 6 is 24. So we have plus 24, and it comes out to be 24 plus 24 is 48 minus actually it is 0 here because we are multiplying with 0, so we are left with these two elements 24 and 24, which comes out to be 48. That means H2 which we got here, bordered Hessian, what we got, the determinant of this we got 48, which is greater than 0. Whenever our bordered Hessian method is greater than 0, we say it is negative definite. Negative definite. Okay, when we have this second border principal minor greater than 0, we say we have a negative definite determinant, and this negative definite determines or satisfies the sufficient condition for relative maximum. Okay, so negative definite satisfies the sufficient condition for relative maximum. Okay, so that means second order condition is also fulfilled, and we make sure that these x is equal to 15, y is equal to 11.2 are actually at their relative maximum value. Okay, I hope I make myself clear in this video. How do we solve for the bordered Hessian method? First, we take the utility function and the budget constraint. We use the first order condition for Lagrange first order condition, and first order condition is satisfied. First we form the Lagrange's function. How is Lagrange's function formed? We take the budget constraint, set it equal to 0, multiplied by lambda. this very thing, and to this we add our objective function. Then we need to satisfy the first order condition. First order condition is satisfied if we take the partial derivative of this Lagrange function with respect to x, y and lambda and set them equal to 0 simultaneously, and solve for the optimal value of x, optimal value of y and optimal value of lambda. Okay, after that we got the optimal values of x, y and lambda, and in fact this lambda is called the shadow price. It only tells us how much our utility will change if the constant changes by 1 unit. Okay, now after that, since we got the optimal values but we are not sure whether we are at relative maximum or relative minimum, it only tells that we can afford these very bundles. Okay, to check the second order condition we use the borrowed Hessian method. How do we form the borrowed Hessian method? It is very simple. Borrowed Hessian method is formed. First we form the Hessian matrix. Hessian matrix is a determinant composed of the second order partial derivatives with second order direct partials on the principal diagonal and second order cross partials on of the principal diagonal. And to this simple Hessian, when borrowed by the first derivatives of the constraint function, this is our constraint function, then we get this very borrowed Hessian matrix. Of course 0 is on the principal diagonal. After that we just need to take find the value of lxx, that is the second derivative of this lx. Similarly lxy, lyx and lyy. I have shown you how do we take the second derivative. It is very easy, and I have shown you how did I take this. After that we need to check what is the value of the determinant of this second border principal minor. Okay, so this second border principal minor is actually equal to our Hessian. Okay, Hessian matrix, which is H2. We got it equal to 48, which is greater than 0 whenever we have the the determinant of the Hessian matrix greater than 0. We say it is negative definite, and negative definite satisfies the sufficient condition for relative maximum. I hope I make myself clear in this video. If you like these videos, please share, subscribe. This is only motivation for me to make more useful stuff for you people. Thank you.